So my name is Ager. I'm a software engineer at Google, and I work on the V8 JavaScript engine. And this talk is going to be about the internals of V8. So what did we do to make V8 fast, and what were our design decisions when making V8? So here's the agenda of the talk. So the main part of the talk will be about the design goals and the overall goals that we had for V8, and the internals. So what did we actually do? What are the techniques that we used to make V8 fast? And that involves things like hidden classes, native code generation using inline caching, and precise generational garbage collection. So that will be the main part of the talk, where I explain these things. So after that, I'll tell you something about a couple of recent developments in V8. So the first one is that we implemented a new JavaScript regular expression engine completely from scratch. And the other one is that we've built a new compiler infrastructure. I'm just going to briefly mention those and tell you a bit about them. And then I'll go into something that I think is really important. And I've called it object heap scalability here, or JavaScript scalability. And that's all about how well your JavaScript engine deals with running really, really big web applications where you have a lot of objects. And therefore extra pressure on your memory management system. And I think that this is really important, and I think that it has been underemphasized so far. So I'm going to spend a bit of time talking about that. And then at the end, I'm going to just tell you a bit about some of the performance bottlenecks that we have in V8 right now, which will give you sort of an indication of the kind of things that we like to work on in V8 to make it even faster. Okay, so for this talk, the first question is really, why did Google want to build a new JavaScript engine? And the answer is pretty simple. So we believe that in order to build the next wave of big web applications, you need better JavaScript performance. And at the time when the V8 project started, the existing JavaScript engines were not very fast. So basically, they were all interpreters working on abstract syntax trees or on bytecodes. And they had poor memory management systems, which led to big pause times and maybe even memory leaks. So we wanted to try to change this picture. We wanted to try to push JavaScript performance. And we thought that the best way to do that was to build a completely new JavaScript engine from scratch so that we could do our own designs and start completely from scratch. So the overall goal for V8 is to push the performance bar for JavaScript, not only for Google Chrome and for V8, but we wanted to kind of try to push the industry and see if we can get better JavaScript performance in browsers in general, which will benefit all of us. It'll benefit Google because we can do better web applications, and it'll benefit the users as well because, well, users write web applications as well. So we wanted to build a really fast JavaScript engine. So why is that a challenge? Well, JavaScript is a very, very dynamic language. So objects are basically just hash maps. So you can add and remove properties to and from objects on the fly in any order you like. And you have no type structure. So if you want to do a property lookup on an object in JavaScript, you don't know anything statically about the object. So if you have an object, you want to search for the X property, you have to do exactly that. You have to search. So you have to look in your hash map. If it's not there, you need to traverse the prototype chain and look for it there. And that's like really slow. So if you compare that to static, object-oriented languages, where you have a notion of type, where you have classes, if you do a property load in a language where you have a notion of class, well, then the class tells you the layout of your object. So if you want to access an X property on an object that has a certain class, then the class tells you the index in your object for that property. So you can generate just a few assembly instructions that will load your property. In JavaScript, if you just do it like naively implement JavaScript, then you'll have a full search of a number of hash maps in a chain. And that's really slow. Right, so JavaScript is highly dynamic. You can add properties to objects. You can remove properties from objects. And you can actually change prototype chains as well dynamically. So you can change basically everything in your program on the fly. Also, JavaScript has a couple of language features that could give you trouble as well. So one of them is eval. So eval is a function that you can call with a string to evaluate that string as JavaScript code. And that's actually not so bad. The problem with it is that it can also change the calling context. And that means that if you're trying to implement JavaScript, you really want to have some scope information. So if you access a property X somewhere, you want to be able to see basically in your scopes where is X declared. But if you have a call to eval, basically you don't know, because eval can introduce new bindings dynamically. So you could introduce a new X variable in the context where you're calling eval. So basically you just have to give up and say, statically, I don't know. And there are similar issues with statements in JavaScript. So with statements are used to introduce a new object in your scope chain. So if you want easy access to all the properties on the document object, you can say with document, and then have a block of code, where if you just write a name, like write, that will be looked up in the document object. So that will actually be document.write. And that's all fine, but if you want to have scope information again, you have to give up inside of a with statement, because you don't know. Because it might look like a variable is declared in an outer scope, but dynamically, you might introduce an object with your with statement that has that property name as well, and that's the one that you need to get. So overall, JavaScript is very dynamic, and that makes it a bit of a challenge to implement it efficiently. So let's talk about what we did for V8 and which design decisions we took. So the goal for V8 was to create a JavaScript engine that would make large object-oriented applications perform well. So if you have large object-oriented applications, you're going to use abstractions. And if you use abstractions, you're going to have a lot of property accesses, and you're going to have a lot of function calls. And you're going to have a lot of objects. So that means that in order to make these kind of applications run fast, you need fast property access, you need fast property calls, and you need fast and scalable memory management. So you want to be able to handle a large number of objects efficiently. So these goals led to 3 key components of V8. So the first component is something called hidden classes and hidden class transitions. So hidden classes is basically our notion of types. So JavaScript does not have any types, and we're not adding types to JavaScript or anything like that. But internally in the JavaScript engine, we have a notion of type, and that's our hidden class. And I'll tell you more about that. So once we have that, we can use a technique called inline caching. So we generate native code for all of our JavaScript, and we also generate code on the fly and use a technique called inline caching. So these two things together, hidden classes and native code generation with inline caching, gives us fast property access and fast function calls. So those are the 2 first items. So the second thing that we wanted was a fast memory management system. So we use a generational garbage collector. And it's pretty much standard, but it works really well. And that means that having a generational garbage collector, we scale well to dealing with a lot of objects. And I'll tell you some more about that as well. Okay, so let's dig in. So to set the scene, let me start by telling you a bit about V8's memory model. So in V8, we use 32-bit tag pointers. All of our objects in our heap are 4-byte aligned. And that means that if you have a pointer to a JavaScript object, the 2 least significant bits are going to be 0. So we can use that knowledge to actually do pointer tagging. So since we know that all pointers should have the 2 least significant bits 0, we can actually put in 1s there to give some extra information to our pointers. And then we can just make sure to strip them if we actually need the actual pointer. So what we use that for is allowing 32 31-bit signed integers to be immediate values. And they're distinguished from real pointers by tagging. So if you load a pointer to a JavaScript object from a heap, and the address is even, it's actually not a pointer. It's an immediate integer value, and you get the integer value by just shifting 1 bit right. So basically shifting the 0 away, and that's going to be your integer value. So that means that we can have we can deal with integers efficiently because they're just immediate values, and we don't have to do any heap allocation to handle integers. So on the other hand, if you load a pointer to an object from our heap, and it's odd, so it has the least significant bit of 1, then it is an actual pointer, and the pointer to the object is this value where you subtract 1, so where you clear the tag. Okay, so our base JavaScript objects consist of 3 words. The first word is a hidden class pointer. So this is our notion of type, as I told you before, and I'll get into details on that in a second. And the 2 other pointers are used to point to where we actually hold the values of properties. So we split the properties backing storage into 2 parts. One is for properties that are named by strings, so like X, Y, and Z. And the other one is for what we call elements, which are basically properties which have integer names, so 0, 1, 2, and so on. So all of our JavaScript objects are these 3-word thingies. Okay, and the backing storage for properties and for elements can be in 2 different states, namely a fast case and a slow case. So in the fast case, a properties backing storage or an elements backing storage is just an array where you can do direct indexing. And in the slow case, it's going to be a dictionary or a hash map. Okay, so now we're ready to talk about hidden classes. So, as I told you, in static object-oriented languages where you have classes, you can do really fast property access because the class describes your object and you know exactly where to find the properties of your object. So we wanted to have the same ability for JavaScript. We wanted to be able to do like a few assembly instructions to load a property. So to use these normal optimization techniques, we needed to introduce a notion of type. And for that, we use hidden classes. So hidden classes are classes, but they're only internal to the JavaScript engine. So it's something that we keep track of and users don't know about. And hidden classes group objects that have the exact same structure. Okay, so talking about hidden classes, it's easiest to just have an example. So in JavaScript, all objects are created from functions. And here's a point function, which is a constructor function that we can use to construct points. And it just takes 2 arguments and assigns them to the x and y properties of the resulting object. Okay, so the goal here is that any point that we construct should end up having the point map, basically, the point hidden class. So JavaScript objects created in the same way should end up having the same hidden class because they'll have the same internal structure. Okay. So in this example, I'm going to create 2 points. I'm going to show you how they end up having the same hidden class. So since all JavaScript objects are created from functions, we create an initial class for each function. So the point function here is going to have an initial class, which is called class 0, which I've put up there. And this is the class, the hidden class, that we're going to give to all new objects created from the point function. So when we create our first point here, P1, that's this 3-word thing that has a pointer to a hidden class. And since this object was created using the point function, its initial class is going to be the initial class of the point function, class 0. And then it has properties and elements as well. And in the beginning, we're going to allocate a small piece of backing storage, both for properties and for elements. So that's the initial thing that you get when you say new point. And then we're going to start executing the body of the point function, with this newly allocated object as the this pointer. Okay, so the first thing that we're going to do is add an X property to this object. So adding a property to an object changes the structure of the object, which means that we need to change the hidden class of the object. So when we assign X to this property, we need to create a new class. And we do that by copying the original class, which is class 0, and then adding the knowledge to that class that we have an X property, and that property is at offset 0 in our backing storage. And then we're going to put the value into the backing storage at offset 0. And importantly, we're going to remember in class 0 that if you have an object that has class 0 and you add a property with the name X, then you need to transition to class 1. So that's what we call a hidden class transition. And now a similar thing happens when we add the Y property. So adding a new property to an object changes its structure, and therefore it needs to change its hidden class. So we create a new hidden class by copying class 1. We add the knowledge that we have a Y property, and that the value of the Y property is at offset 1 in our backing storage. We fill in the value, and we update the hidden class pointer to point to this new class. And again, we remember in class 1 that if you have an object that has class 1 and you add a Y property to it, then you need to transition to class 2. Okay, so that finishes the construction of our first point. So you see, this is actually pretty heavy weight to construct the first object from a constructor function, because we need to create all of these new classes by copying existing ones and adding a bit of information. But that only costs on the first construction. So on the next construction, we're basically going to do the same thing, but we're going to reuse our classes. So if we go to the construction of P2, that will create a new object, which is this 3-word thing. The initial class is going to be the class associated with the point function, which is going to be C0, class 0. And then we're going to execute the body of the point function. So the first thing we're going to do is is to add an X property to our object. So now, this point has class 0. And in class 0, there's information that if you have an object that has class 0, and you add a property called X, well, then you need to transition to class 1. So that's what we're going to do. So for the assignment to X, we're just going to update the hidden class pointer and put the value in the backing storage. And similarly for Y, we now have an object of class 1. In class 1, we know that if you add a Y property, you need to transition to class 2. So that's all we're going to do. We're just going to update the hidden class pointer and add the value to the backing storage. So now we've created 2 point objects. They've been created in exactly the same way, and they end up sharing the hidden class, class 2. And the important thing here is that in class 2, we have a complete description of our objects. We know that all objects that have class 2 will have X at offset 0 in the backing storage and Y at offset 1. And we can use that to optimize property accesses. So let me revisit my previous statement. So I said that JavaScript is really challenging to implement because it's really, really dynamic. And that's true. So in JavaScript, you have a lot of features that allow you to write really, really dynamic code. But it turns out that if you write nice, well-factored code, in most cases, you'll have like parts of your code that deal with objects that have a certain structure. So now that we have hidden classes, we can instrument our JavaScript engine to actually collect information about the hidden classes that hit certain access sites. And it turns out that 90% of the cases, or maybe even more, only objects having the same hidden class are ever seen. So that means that basically you know something about the structure of your objects when you've seen an object once at an access site, and that's what we're going to do to optimize. So basically, at runtime, JavaScript is not that dynamic. You basically see things that have the same structure again and again and again and again. So we can use that. So the only problem here is that when we generate the JavaScript code, the native code, for our JavaScript code. We don't know the hidden class of an object at an access site because we have no type information in the language. So that means that we only know something about our objects when we see the first object at an access site. So in order to handle this, we use runtime code generation, and we use a technique called inline caching. So here's a very simple picture of what inline caching is like. So in the beginning, we just generate native code for our JavaScript code. And at all access sites, we have absolutely no knowledge. So if we want to load an X property, we're just going to call a piece of code that's going to do a completely generic full lookup through our objects to see if it can find the property. But once we've done that once, we have some extra information. We know the hidden class of the object that we've just looked at, and we know where we found the property in this object. And based on that knowledge, we can generate a small snippet of new code that's going to be really fast, and it's going to assume that the next time we get here, we're going to see the same hidden class again. So then we're going to rewrite the code so that at this access site, we're not going to go to the fully generic code, but we're actually going to hit the fast lookup code. And the only thing the fast lookup code has to do is validate our assumptions. So it needs to check that the next object that gets here actually has the same hidden class as the first one. And if it does, then it knows exactly where to load the property value. OK, and if the assumptions are broken, so if we get here with another type of object, well, then we bail out, and then we go to the fully generic lookup again. And again, that's the same for all access sites. When we see in the first object at an access site, we generate a new piece of code to do a fast lookup the next time. And that's with the assumption that we get the same hidden class again. If we don't, then we bail out and do a full generic lookup. OK, so what does the fast case look like? So it looks like this. And I've actually given you all of the information that you need to completely understand what's going on here. So let me try to step through it. So this is the small snippet of code that we generate to access a property on an object. So the first couple of lines here. The first line just loads the receiver from the stack into register EAX. Okay? So as I told you, we use tag pointers. So now we've loaded something. Okay? So now we need to check if it's an object or if it's an immediate value, maybe a small integer. So that's what the second line here is doing. It tests if the least significant bit of EAX is 1. If it is, this is an object pointer. If it's not, it's an immediate integer value for which this snippet doesn't really do anything. So we're going to jump out and go to the generic case if that's happening. So if we see an integer here, we're just bailing out. So the first lines here are just loading the receiver, checking that it's an object. So the next couple of lines here are validating our assumptions. And our assumption is that we're going to see the same hidden class again. So this piece of code was generated with the knowledge that that the hidden class of the first object that got here was at address whatever's there, 0xF78, and so on. Okay. So now we need to check that the hidden class of our current object is the same one. So we're going to load from EAX -1. So that's removing the tagging from the pointer and loading a pointer from there, which is the map pointer, and we're just comparing that to what we saw before. If it's the same, we're happy, and we load the properties array from our object, and from the properties array, we load the property value directly, and then we return. So in the fast case, all we need to do is check our assumptions. We load the receiver, check that it's an object, check that it has the correct hidden class, and then directly load the property. So that's a few assembly line instructions, and that's really, really fast. And if any of our assumptions break, if we either get an integer or if the class does not match, then we bail out and go to a fully generic lookup. Okay, so basically, I've told you now about 2 states that our inline caches can be in. There's actually a third as well. So the 3 inline cache states that we have are uninitialized, which is where everything begins. We don't know anything yet. We haven't seen any objects here. So once we see the first object, we transition to monomorphic, which means that we've only seen one hidden class at this access site. If we see more hidden classes at the same access site, we go into what's called a megamorphic state. And that just means we've seen more types here. And in that case, we actually use a cache of generated fast case stubs. So if we've already generated a stub for this hidden class that we're seeing and this property, we use that. And otherwise, we go to the full generic lookup. So even if we see multiple different classes at the same access site, we're actually trying to use some of our optimized stubs. Another thing worth knowing about inline caches in V8 is that we clear them on full garbage collections. And that might sound odd. So we've just spent time generating code on the fly, and now we just throw it all away. So the reason for that is that, first of all, it allows us to get rid of unused code stubs. So all of the code that we generate is allocated in the JavaScript heap, like any other JavaScript object, and it flows freely around. So in order to be able to throw it away, we need to clear our inline caches, so there are no pointers to these stubs. So if you have an application where you have like a couple of stages. So in the first stage, you set up a lot of stuff, and you do a lot of things with one piece of code, and then basically you transition to some other, to like another phase where you use basically another piece of code. We don't want to keep all the code objects alive from the first piece of code, because if they're not going to be used anymore, that's a waste. So clearing inline caches at full garbage collections allows us to get rid of unused code stubs. The other thing that clearing inline caches at full garbage collection gives us is the ability to actually go back to the fast case if we hit the slow case, where we've seen multiple different hidden classes at an access site. But basically, we've transitioned to another phase of the program where we're only seeing objects with the same hidden class. Then we basically don't want to get stuck in the situation where we think that we've seen multiple things. So clearing inline caches on full garbage collection gives our inline caches the ability to go back to the fast monomorphic case again. Okay, so that was an introduction to how we make property accesses fast. So there are two things here. There are the hidden classes and the transition between hidden classes, and there's native code generation with inline caching. So the next thing I'd like to tell you about is our memory management. So we use a precise generational garbage collector, and what we really want here is to get in a situation where the JavaScript engine scales well. So if you have a lot of objects and a lot of big data structures when you run your program, we don't want the garbage collector to have to look at all of these objects every time it has to reclaim some memory. Because that's going to lead to big pause times, and it's going to degrade your performance, because every time you need to get some free memory, you have to look at everything. So we don't want that. So instead, we use generational garbage collection. So we have two generations. We have a young generation, which is one small contiguous space, which we garbage collect often. And then we have an old generation, which is divided into a number of spaces. And we only occasionally garbage collect the old generation. So the reasoning here is that in object-oriented programs, most objects that you allocate are going to be dead really soon. So you'll have a lot of temporary objects. And the ones that do not die immediately are often long-lived. So we allocate all of our objects in the young generation. When we run out of space in the young generation, we need to do a garbage collection. But we only garbage collect the young generation. And since most objects that are allocated die really young, there'll be a lot of dead objects in our young generation. So we can get rid of most of them, and then we'll be ready to allocate again. So there's no reason for us to look at the old generation if we can free enough memory from the young generation. So objects that survive in the young generation will be promoted to the old generation. And then we'll continue. Okay, so the old generation, as I said, is divided up into a number of spaces. I'm not going to go into a lot of details with that, but so the reasons for having multiple spaces is basically to be able to manage the bookkeeping in our memory management system. So for instance, we have pages that are 8K big. So if we have objects that are larger than that, then we're not going to allocate them in the normal way. So we have a special space for large objects. And also, as I said, we're dynamically generating native code on the fly. So we need one space that's executable, where we generate our native code and run it from there. So that's the code space. And then there are a number of other spaces. Good. So which types of garbage collection do we use? I'm sorry about that. My slides are a bit messed up here. I think we'll be fine. So we have three types of garbage collection. So the first one is a scavenge scavenge. And on a scavenge collection, we only look at the young generation. So this is what we do all the time. And that's a copying collection, which means that it's linear in the size of the live data. And as I told you, a lot of data dies, a lot of objects die really young. So that means that most of your data in the young generation is going to be dead. And since this garbage collection technique is linear in the size of live objects, it's going to be really fast because there's not going to be much live data. So typical pause times for a scavenge is 1 to 2 milliseconds. And we do that all the time. Okay, so once in a while, we've actually promoted enough objects that we should try to clear up the old generation as well. So once in a while, we do full garbage collections, and we have two flavors of those. So the first one is a non-compacting collection. So that's a mark sweep collection of both young and old generation. And in the non-compacting version, all free memory gets added to free lists, and we allocate from there. And this might cause fragmentation. So fragmentation is not good. So that's why we have another way of garbage collection. Okay, so a typical pause time for like really big applications for a full non-compacting collection is up to 50 milliseconds. Often you'll see a lot smaller, but if you're building really big applications, you can see pause times up to 50 milliseconds. So the last type of garbage collection that we have is a full compacting collection. And that's a mark sweep compact collection of both generations. And instead of adding free memory to free lists, we compact everything. So we move all of the objects to the beginning of pages to get rid of the fragmentation. So basically, inside of V8, we have an idea of how much fragmentation we've created. And when we reach a certain threshold, we're going to do a compacting collection to get rid of the fragmentation. Okay, so getting rid of fragmentation means that we need to copy a lot of objects. So if you're building a really large application, you might get pause times of up to 100 milliseconds here. Yeah. Oh, so the question is, how big is the young generation? It's not very big. It's like, wow, honestly, I don't even remember. I think it's a megabyte or two, something like that. So I'm not sure I understand the question. So you're saying that if I have an application that allocates a lot of small objects, and then you're saying that then the young generation is going to be scanned frequently? Well, no, not really. So if you allocate a lot of small objects, yes, they're going to be allocated in the young generation. So when you fill out the young generation and you don't have any more room, you need to garbage collect. So at that point, you look at all the live data, and then it's true that if all of your objects are still live, then you're going to look through all of them, basically. But if they survive, then you're going to move them to the old generation, and you're not going to look at them again. Yeah. But yeah, you're right. I mean, as long as you just allocate, and keep everything alive is going to be allocated in the young generation, and you're going to scan all of them and basically move them to the old generation so you don't have to look at them the next time. Yep. Oh, the timing of these? These are on desktop machines. So basically running inside of Chrome on like a modern machine, desktop machine. Okay. So that covers the part of how we made V8 handle property accesses, function calls, and write really well and be fast at that, and how we made V8 scale by using generational garbage collection. So now let me talk a bit about some recent developments. So recently we've implemented a new regular expression engine for V8. It's called Irregexp. So initially V8, actually in the beginning, like completely from the beginning, to get V8 up and running, we used PCRE, which is a standard library for regular expression matching. The problem with PCRE is that it does not match JavaScript regular expression semantics. So you need something else. Either you need to modify PCRE, or you need to have like a compatibility layer that basically translate PCRE regular expressions, JavaScript regular expressions to their equivalent PCRE regular expression and then use PCRE. So luckily, at WebKit, they had this problem as well, and they created a library called JSCRE, which matched JavaScript semantics. So we switched to that. So the initial version of V8 used a library from WebKit called JSCRE. So JSCRE did not fit V8 that well, so it didn't really perform well. And the reason for this is that JSCRE expected a different string representation than most strings in V8. So in order to actually hand off a string to JSCRE, we would most of the time have to do a string conversion, and that's really costly. So this really didn't perform very well. So, and we thought that we could do better, and we also thought that we could do better when it comes to algorithms for regular expression matching. So we implemented our own regular expression matching, which has given us a 10 times speed up on regular expression matching on our benchmarks. And our new library implements all of JavaScript regular expressions, so there's no fallback to any other engines. It's a full JavaScript regular expression implementation. So what's in there? Well, first of all, the new regular expression engine is based on an automata approach. So from an input regular expression, we build an automaton, and then we perform analysis and optimization on that automaton. And then from the resulting rewritten automaton, we generate native code. So all of your regular expressions are now executed using native code. And in our analysis and optimization phase, we use a number of tricks to make regular expression matching cheaper. So we try to avoid backtracking, and we try to reorder operations so that we perform the least expensive operations first. So when you do regular expression matching, most of the time you do find a match because you actually know that it's going to be there that it's going to be there somewhere. But you start from the beginning, right? And maybe you have to scan through a lot. So basically the common case for regular expression matching is that you don't have a match. So at the first position, you're probably not going to have a match, and so on. So reordering operations to perform the least expensive operations first gives us an opportunity to fail as quickly as possible, which is actually pretty important when you do regular expression matching. Okay, so let me give you a couple of examples here. So one of the things that we do, which is to avoid backtracking, is to search for common parts in alternatives first. So if you want to look for either sun or mon, then the common part of this regular expression is that the character at index 2 is going to be n. Okay, so if you search and at the current position, the thing that's at index 2 is not an n, then you're done. Then you don't have to do anything more because then you know that it can't match here, so you need to move on. Okay, so the more traditional approach here would be to start out by the first alternative. So you try to look for a sun. So you might find S, you might find U, and then you might not find N. And then at that point, all you know is that you didn't match sun. So you have to try the other alternative. And that'll fail by looking at the M, right? But by looking for common parts first, we just have to do one comparison, and we know that it's not going to be here for any of the alternatives. So that avoids a lot of backtracking. Another nice thing about our new regular expression engine is that in V8 we have an ASCII representation for most strings, because a lot of strings that are actually used in JavaScript programs are still ASCII strings. And that means that in a single compare instruction, you can actually match up to 4 characters at a time. So in order to search for foobar, you'll just, in an ASCII string, you'll just load 4 bytes into a word, and then you'll do a compare against a bit pattern that's foob. And then you're going to load the next 2 characters, which are 2 bytes, and then you're going to do a 2-byte compare for those. So that's really nice, to have the ability to actually match 4 characters at a time. That's really fast. Okay, so here's an example that shows you something about reordering. So here's a regular expression that looks for foobar. That can be spelled either with a normal F or a capital F, and a normal B or a capital B. And then it's going to capture whatever was matched. Okay, so we want to perform the cheap operations first. So we're going to try to begin by matching OO and AR at position 1 and 4, because those are just like symbol character comparisons. And those are really quick, and if one of them fail, well, then we can skip all the rest. Okay, so the next thing we're going to do is look for either F or a capital F at position 0, and we're going to look for a B or a capital B at position 3, and then finally we're going to perform the actual capture operation. So the reordering here is really just to get the cheap operations first, because that allows us to fail early and quickly. Good, so that's a new regular expression engine. So another thing that we've done recently is to change our compiler. So the original compiler was extremely simple. Just build an abstract syntax tree. It did no static analysis of any kind. It did no register allocation. So just build an abstract syntax tree, and one pass over the abstract syntax tree, it generated code, period. So we've now implemented a new compiler infrastructure which performs register allocation. It's still a one-pass compiler. So for JavaScript, since you get all of your code over the network, you need your JavaScript engine to be able to run the code quickly. Right? So you need to have a fast compiler. So it's still a one-pass compiler, but now it actually does its best to do register allocation as well. And we're pretty excited about this, and we think that it will form the basis for further native code optimizations in V8. Okay, so that's what I wanted to say about recent stuff. So now I'm going to talk to something that's quite different, but that I think is really, really important, namely how well your JavaScript engines scale to deal with very large applications. So why is that important? Well, so web applications are becoming bigger and bigger and more complex. And with the increased complexity, you get more objects, and more objects put extra stress on your memory management system. So if you do not have a system that scale to handle all of these objects, your performance will suffer. So not only are applications becoming bigger, which means that they get more objects, but also a lot of browsers are still single process. And most single process browsers, when you start up multiple tabs with multiple applications, all of your JavaScript objects are going to be allocated in the same JavaScript object heap, which means that you actually get a lot of objects in your JavaScript heap. So if your memory management system has to look at all objects for every garbage collection, that's going to hurt you. Right, so it is actually really important that your JavaScript execution is good and is fast in these situations as well. And it's important now. It's not only for like the future. It's also important now. Right, so our approach to scalability is to use generational garbage collection as I've just told you about. Right. So I've done a little experiment here, and I should say right now that this is really, really artificial. So take all of this with a grain of salt, but it does illustrate my point. So my scalability experiment was to take the ray trace benchmark from the V8 benchmark suite and then run it a number of times. And on each iteration, I'm going to allocate some extra memory in the JavaScript heap. And with V8, the data structure that I'm going to allocate, I'm going to add 1 megabyte of extra live data per iteration. And then I'm just going to map out the performance, so the benchmark score, over these iterations with an increased amount of objects in your heap. And the result looks like this for 3 browsers. So as you can see, the performance characteristics here are quite different. So what we want to get to here is basically having a straight line. So as you can see, Chromium running V8 is not getting a straight line, but it's also not like dropping completely. And that's pretty much what you get when you use a generational garbage collection like we do. So it does cost to have larger heaps, but your performance does not completely degrade. So another interesting thing that you can see from this graph is that you have like down spikes. So those down spikes are when you get to the full compacting collections. So if you actually get to a point where you need to do a full compacting collection, that's going to be visible on graphs like these. So the interesting thing here is that Firefox 3.5 Beta 4 seems to be doing very well when it comes to scalability. The benchmark score is not that impressive on the other hand. Safari is doing really well on the benchmark score, but it seems that there's something like a full scan of the heap on each garbage collection, because if you add extra data to the heap, then already at like 5 megabytes, they're at a third of the speed that they had with a freshly started browser. So I think this really matters because this is a benchmark, right? So this is a benchmark that's in our benchmark suite. And this tells you something about how valid those benchmark results are in the real world. So if you have a single process browser and you open multiple tabs, that's going to lead to a lot of objects. And then your performance is going to be more like what's on the right of this graph. So I think that we need to put some more emphasis on this. And I think that is really important because it's really important for the real life situations, having many tabs or having big applications. So in order to put a bit of focus on this, we've published a new benchmark in the V8 benchmark suite, which is, again, completely artificial. So it builds a splay tree, roughly of the size of like 30 megabytes or something like that. And then it just performs operations on the splay tree, which means that it allocates new nodes, it modifies the splay tree, and it garbage collects nodes that have been removed. Right, so we really want to try to put some emphasis on this. We want scalability. We want browsers to be scalable. We want people to actually get the JavaScript performance that they expect when they run the JavaScript benchmarks out there. Those should basically reflect what you get in reality. So again, this experiment is completely artificial. If you want to try this, take your browsers, load a number of tabs, run benchmarks, or try something else. Try writing really big web applications and see how well JavaScript behaves under a bit of stress. Good, so that finishes my scalability rant. Good, so let me tell you a bit about the performance bottlenecks that I see for V8 currently. So one of the bottlenecks that we have is that we only generate one fully general version of all code that we generate. And that means that we are not basically allowed to have that many assumptions in our code, because we need to handle all the special cases in the code that we generate. So that means that we have a lot of checking for basically exceptional situations in our code, like situations that basically do not happen in reality. So one thing that we should explore is generating multiple versions of the same code. So generating, in the beginning, generating really optimized version of the code that avoids a lot of the checking. And then if some of our checks fail, then basically bail out to a slower version of the code. So at that point, generate another version of the code. So that should give us a big performance gain. Another bottleneck is that our use of inline caching is based on calls to stubs. So we generate these stubs, and then we use like a call instruction to actually get to that code. And that's good for a code size, because we can just have a call instruction in there. But it's not necessarily the best thing we can do for performance. So in some situations, we might actually want to inline the code instead, directly in the code stream. So instead of having the call, we can just have the code directly there. And that actually matters. And we have done that for a couple of simple cases of loads. And it really does matter. So the downside to that is code size. So your code becomes bigger when you actually inline. Okay, so another issue, which is basically related to doing more inlining, is our write barrier. So since we use generational garbage collection, and we garbage collect the young generation often, we need to know about all pointers into the young generation. And that includes all of the pointers from objects in the old generation to pointers in the new generation. And that means that whenever we store a pointer in an old generation object, we might have to record somewhere that this object is actually referring to a new space object. And that's done by something called a write barrier. And right now, our write barrier is a bit complicated. It has a lot of instructions, and it's a bit slow. So we should experiment with new ways of implementing our write barrier. And the reason why that's related to inlining more code is that since our write barrier is pretty big, it's not really practical to inline stores directly in the code, because all stores need to have the write barrier inlined as well. And that will lead to a lot of code size increase. Again, the last thing here, I don't really want to talk much about, but basically there are a lot of global loads in JavaScript code, and we handle global loads the same way as any other loads, and basically we don't have to, so we could generate better code for that. So another thing that I didn't put up here, but which is also really important, is DOM performance. And basically we haven't done much in that area to really, really optimize it. So that's another thing that we should do. We should look more at DOM performance, so the interaction between JavaScript and the DOM. Good. So to summarize, V8 was designed both for speed and for scalability. The goal of V8 is to raise the performance bar for JavaScript. So we want to continue to push and see if we can make JavaScript even faster. We don't want to just push for Google and for Google Chrome. We really want to try to see if we can inspire other JavaScript vendors as well. And therefore, our full source code is available under a BSD license. And unfortunately, the URL scrolled out of my slides here. But it's at code.google.com/p/v8. Should be pretty easy to find. So the graph that I've put up here that I'd like to end with is what has happened to the V8 benchmark score over time. So the versions that you see on the left are Google Chrome versions. So this basically started in September of 2008 with a 1.0 beta. And since then, we've just continued to push, and we will continue to do that. So that's all. Thanks. Questions? Yes? Yeah, that's a good point. So the question is, in my example of hidden classes and hidden class transitions, I added first X and then Y. So what would happen if I added Y first and then X? And the answer is that that would be a different hidden class. It's really common for objects to be generated in exactly the same way. So that's basically what saves us. But you're right, that objects that basically have the same structure, namely a y property and an x property, they can actually get completely different maps if you first add y and then x, and then in another place add x and then y. Those will be separate hidden classes. Yeah. Okay, so what if you declare an object through an object literal and not through a function? That's not going to be a problem, because object literals are also created based on a function, namely the object function. And the object function has an initial map. So basically, the same thing works. Yep. Yeah, that's a good question. So the question is, do we only apply this to user-defined objects, or do we also use this on like built-in stuff like date, math, number, whatever? And the answer is that yes, we also do it on built-in stuff. And to go a bit deeper, our built-in stuff is actually implemented in JavaScript. So we don't implement that in C++. We actually have it implemented in JavaScript, a lot of it. So that means that basically the same thing applies. So it's going to go through exactly the same path. And the cool thing about that is that if we improve our overall JavaScript performance, we're also going to improve the speed of our libraries. So that's one cool thing about having libraries written in JavaScript. Another cool thing is that it's really easy and quick to go change stuff. So it also does lead to some extra complication in the sense that in order to set up your math, number, date objects, you actually have to look at JavaScript code. You actually have to compile JavaScript code. So to overcome that, we use something called snapshotting. So yeah, so this is becoming a longer explanation. Sorry about that. So basically, in the beginning, the first time so when we built V8, we start up V8 once. We load the basic libraries. That gives us a heap that contains all of the code for our basic libraries. We dump that heap as a binary image to a file, and then we integrate that binary data into a new version of V8 that we built, so that when you start V8, even though your libraries are written in JavaScript, you don't have to parse and compile any JavaScript code to get your native libraries. All you do is just slurp in that binary data, and you're up and running. Yep.
Are there any design patterns that you know of that perform better than others? JavaScript design patterns?
So the question is if there are any JavaScript design patterns that I know of that perform better than others. So my answer to that would be no. But also my answer to that should be that it shouldn't matter that much. So basically, you shouldn't worry about it. We should hopefully be able to make it fast. But as you've seen with the techniques that we use here, we're kind of somehow relying on you to do something that's like well-structured and uses abstractions and does not like try to be overly general and try to have like code that's like really using operating on a million different types. But that shouldn't really be an issue, because in most application code that you write, you might have parts of the code that's like that's really generic, and then you have most of your code, which is not. So basically, you shouldn't have to worry about it. That should be us worrying.
Any?
Oh. Okay, so the question is if I can give some information about other browsers that are using these techniques, and also if it's being fed back to WebKit. Yeah. So Apple's JavaScript engine, I guess it's called Nitro by now, is using these techniques as well, which is really cool. So I think that's great, and they're getting great performance gains the same way that we did by using these techniques. So they use what we call hidden classes and inline caching as well. I think they call their hidden classes structure IDs or something like that, but they use the same techniques, which is really cool. Feeding it back to WebKit, yes, we are doing that in the sense that the binding layer, so the layer that binds V8 into the DOM, is being upstreamed to WebKit. So that actually lives at WebKit now. So hopefully it should be fairly easy going forward to use V8 instead of Nitro if you want to in WebKit.
Over here.
Oh, yes.
Any performance boost to the Lambda functional closures, optimizing the call stacks?
So I'm not sure I understand the question. Could you repeat, please?
Is there a performance boost to the handling of the Lambda functions closures?
Oh, if we have any performance boosts on closures. Well, basically, I mean, that code is handled like all other code. So it gets like the same kind of benefits that the rest of the code does. So yes. So I think we're running out of time. So I think I should stop now. So you're all welcome to come talk to me afterwards. So if you have other questions, please come talk to me.